One very useful way of working with random signals is to model them in terms of linear time invariant systems. So the idea is that we observe a random signal, say described by a time series x of n, and we want to find some model that describes the properties of this signal x of n. We're not saying that x of n was actually produced by the model, but rather that the model describes the properties of the signal. This is a topic that's often addressed in the context of time series analysis, and our approach here is we're going to have a linear time invariant system described by a frequency response h of e to the j omega and represent our signal x of n as the output of this system when the input is given by white noise. So the power spectrum of the input is just a constant for all frequency. And then if we look at the properties of passing random signals through linear time invariant systems, we see that the output power spectrum is just the product of the input power spectrum, which in this case is a constant, times the magnitude squared of the frequency response of the system. So by changing the frequency response of this system, we can represent many different types of power spectra using this particular framework. So there's three different cases that are commonly referred to. The first one is so-called autoregressive or AR system model. And in this case, the frequency response of the system only has poles. So this h of e to the j omega is a frequency response of an all-pole system. In the second case, we have a moving average or MA system. And in that case, the frequency response corresponds to a system which only has zeros. In other words, there's no poles allowed in the moving average case. And then in the third case, the autoregressive moving average, or ARMA, ARMA, the system that we're using in this box has both poles and zeros possible. By choosing one of these three cases, we can represent different types of spectra or frequency properties for our random signals. So we're going to begin with the autoregressive case, and in this case the difference equation describing the system is, as I've written here below, x of n plus a1 x of n minus 1 and so on plus an x of n minus n is equal to w of n. So the output x of n of the model is a recursion on past outputs, just a linear combination of the past outputs. And then we have the input w of n. Now, if you look at the frequency response of a system described by this difference equation, it's easy to show that it's given by h of e to the j omega is 1 divided by the sum from k equals 0 to n ak e to the minus j k omega. So by changing these a's, we change the frequency response in the denominator. The frequency response in the numerator is 1, and we can't do anything about that. So that's why this is called an all-pole system, and we could write it in terms of poles if we were to use the z-transform representation for the system function. We're not going to do that at this moment. So autoregressive models, it turns out, because they have poles, they're well suited for resonant or peaky spectra. Basically, we can make this quantity small, and when this goes to 0, we get sort of a 1 over 0 effect, and we get a peak at frequencies where that happens. So if we look at the kind of spectra that we model, we see that they typically look like this. They'll have a broad, shallow dip in between peaky sections of the spectra. And these peaks are where poles get relatively close to the unit circle at those frequencies. Now the moving average or all zero system model has a difference equation where the output of the system, x of n, is simply a weighted combination of past values of the white noise input. In this case, the frequency response is just the sum from k equals 0 to m of bk e to the minus jk omega. And this type of a model has zeros. By choosing the bk, I can make this quantity go to 0, which is why we say that this system has zeros. It doesn't really have poles because I can't choose finite values for bk and make this frequency response go to infinity. So when we have zeros, we end up with nulls in the spectrum, or sharp dips, as opposed to the broad valleys that we had in the autoregressive case. But now we get smooth mountaintops rather than peaks. Before we had a denominator going to zero that led to a peak. So we have these nulls that characterize the spectra, and then these broad humps in between nulls if we use a moving average model. Now, the autoregressive moving average case has both poles and zeros, and this is the most general of all. And the difference equation in this case has a recursion in terms of past values of the output of the system involving the a sub n's, as well as a weighted combination of the white noise input to the system, which is where the parameters b sub 0 through b sub m come in. The frequency response has a term in the numerator associated with the bk's and a term in the denominator associated with the ak's. So in this case, I have both poles and zeros, and I can achieve a very flexible, arbitrary sort of frequency response because I can represent both resonant peaks and spectral nulls in the power spectrum. So we can have a situation like I've illustrated here, where I've got a sharp peak at a particular frequency, then I have a couple nulls, and then another sharp peak, and so on. Because we have the ability to place both poles and zeros by changing the AKs and the BKs. So it would seem that this is the most general case, and therefore that why bother with the other cases. Turns out that although the ARMA model is the most general, the autoregressive is the easiest model to find given our observations x of n, or the signal that we wish to model. It's conventional to look at the error between a model for the system and the data itself. If I rearrange my difference equation, I can write it that W of n, which actually represents my white noise input, but I'm going to write it on the left-hand side, that can be given as the difference between x of n, the current value of my time series, and this prediction, which uses past values of the time series. So we're saying that we can view this as a prediction of x of n given the past values. And a good model is going to have a small difference here, a small error, and therefore this prediction does a good job of representing the current value of x of n. So if I want to find a set of A's that will do a good job of predicting with the current time series x of n, it turns out this is easy to solve in this formulation because the squared error, and I know that's the input in the sense of the model, but when we're looking at actually finding the parameters of the model, it makes sense and is more useful to regard this as an error term. This error term, when I square it, is a quadratic function of the unknown AKs. Because on the right-hand side, I know the x's, that's the data that I observe, and then the AKs are unknown. So when I square this, I get a quadratic function, and quadratic functions have unique minima, and it's very easy, therefore, to find the solution that minimizes a function of the squared error. Now, in contrast, if we look at the ARMA model, can write this in terms of the same sort of prediction and error, but now the prediction involves, in terms of the BKs, unknown values of the past input, because this is not something we observe, this is a part of the model. And in this case, if I square W of n, look at the squared error, I end up with a non-quadratic function of the AKs and the BKs, and there's in general no unique solution to minimize this squared error. And in particular, this performance surface, the squared error, has multiple local minima, and therefore it's a difficult numerical optimization problem as well. So even though ARMA is the most general, AR finds perhaps more use because of how straightforward it is to find this model. So remember, we're describing the properties of the signal as an output of a linear time invariant system with noise, white noise, as the input. It doesn't mean that we're assuming our data actually was obtained by this in the same model as a physical mechanism for generating the data, but rather that's a way of describing the properties of the data.